Hello everyone and welcome. My name is Darmina binti Muhammad Faisal from AS203 for S2 and I will be presenting an overview of electricity and magnetism with a focus on vector analysis and static electric fields. Let's begin with a basic. A vector is a quantity that has both magnitude and direction, like force, electric fields, or current density. On the other hand, a scalar only has magnitude, like time, mass, or electric potential. Understanding the difference is essential because electromagnetism heavily relies on vector quantities. Let's look onto the unit vector. What is a unit vector? Unit vector is a vector with a magnitude of 1 pointing in a direction of a given vector. It helps us express vectors in standard direction, which is crucial when working in different coordinate systems. There are three main coordinate systems used in vector analysis. The first one is Cartesian coordinate system, where it uses x, y, and z axes. Vector A in Cartesian coordinate can be represented by its component or as a summand of its component along the unit vector. The second one is cylindrical coordinate system, where it uses radial distance called rho, angle phi, and height as z, useful for cylindrical objects like wires. Since it's an orthogonal system, means its coordinates are mutually perpendicular. This is the vector A representative, and this is the magnitude of the vector A for cylindrical. Meanwhile, these are the dots and cross product. The transformations between Cartesian and cylindrical coordinate are shown here. Now we look forward for the spherical coordinate system, where it uses radius as r, polar angle as theta, and azimuthal angle as phi. This coordinate system great for dealing with point charges. These are the vector and the magnitude of this coordinate system, while these are the dot and the cross product. These are the transformations formula for Cartesian to spherical coordinates, and these are the formula for spherical to Cartesian coordinates. Now let's talk about the unit vector relations between coordinate systems. When switching between coordinate systems, we also need to convert unit vectors because the direction basis changes. For example, in Cartesian we use ax, ay, and az. But in cylindrical, it becomes arrow, a phi, and az. And in spherical, we use ar, a theta, a phi. To solve the problems involving electric or magnetic fields in different geometrics, we convert unit vectors using trigonometric relations. For example, to convert from Cartesian to cylindrical, we use this formula. This conversion let us apply vector operation like gradients or divergence correctly in any coordinate system. Maxwell's equations are the foundations of electromagnetism. They describe how electric and magnetic fields behave. There are four of them. The first one is Ampere's laws, Faraday's law, Gauss's law, and non-existence of monopole. For static electric fields, we mainly focus on Gauss's law and electric potentials. Now we will look for Del operator. The symbol of Del operator is here. It is used to calculate the gradient, divergence, curl, and Laplacians of vector fields, which help us to apply Maxwell equations in vector forms. To find the gradients, it tells us the directions of the steepest increase in a scalar field. Meanwhile, the divergence, it measures how much a vector field spreads out from a point. Meanwhile, the curl quantifies the circulations or rotation of a vector field. Lastly, Laplacians, it measures the concentrations or diffusions of a field, vital for potential and wave equation. Moving to static electric fields, these are the simple fields created by stationary electric charges. They describe the force experienced by other charges nearby. The law of electric charge says that the same charge will repel and the opposite charge will attract. Specifically, in Coulomb law, it states that the electric force between 2-point charge is inversely proportional to the square of the distance between them and directly proportional to the product of their charges as shown in the formula. The electric field is a vector field around a charged particle. It shows the force that a positive charge would feel at any point in space. If the source charge is positive, the field points away. If the negative, the field points inward. In real-world application, we often deal with continuous distributions of charges, not just point charge. In such cases, the total electric field is calculated by integrating over the charge distributions, whether it's a linear, surface, or volumetric. Electric field intensity is the force per unit charge. It shows how strong the field is at a certain point. Meanwhile, electric flux density measures how much the electric field flows through a surface, essentially its electric charge per unit area. These are the equations for electric field intensity, and these are the equations for flux density. Gauss's law relates the electric flux through a closed surface to the total charge enclosed within that surface. It's especially useful for symmetrical charge distributions like a point charge, a line charge, or a uniformly charged sphere. Lastly, electric potential is the work done in a moving unit positive charge from one point to another point. The work done are equal to negative Q integrate A to B of E dl. It's a scalar quantity related to the electric field through the negative gradient. This means the electric field points in the directions of decreasing potential. Thus, V point A to B is equal to negative integrate of E dl. Electric potential directly relates to the Maxwell equation, specifically Gauss's law in differential form. Del operator dot D equals to rho connects the electric fields and the charge density. In conclusion, understanding the vector system, Coulomb law, electric fields, and electric potential give us the tool to solve real-world electromagnetism problems. This concept forms the groundwork for analyzing more complex systems in both physics and engineering. Thank you for listening.